Our next topic in the dry friction section is going to be wedges. So let's put this up here, 8.7 wedges. And the wedge is basically a simple machine that we can use to lift objects. So that's something that supposedly the Egyptians used to lift some of their very big blocks upward, right? So it's a little hard to do. So you can use wedges. We use wedges to split wood. I know that around here, not a lot of wood splitting for heating fires, but when I grew up, that certainly was something, a chore that I used to do. But let's look at an example here, and then I hope that will help us to figure out what a wedge is. So let's say we have this set up right here. We have these surfaces, and then we have another surface coming down like this maybe, and then we have a big object sitting here, big block. And just for the sake of the argument, this has a, let's draw that a little bit longer down. Like that. All right, so this is our big block that we're trying to lift, right? And we'll say this is our block A. And we'll say that this block is secured on both sides by rollers. Rollers here, rollers there, and now underneath sits our wedge. All right, so it's another block with an inclined surface, and that's going to be B. And now we are going to, if we push into this block with a force P, then of course we're going to lift this other block upwards. All right, so that's the idea of a wedge. The idea of a wedge is that we'll use less force to push on here than we'd have to do to straightly lift this up. Right, so that's the whole idea behind the wedge. We have rollers here so that the top block doesn't just move with the bottom block. All right, so let's get a little bit of information more here. So on this surface, we'll have a friction coefficient of mu A. And down here, we'll have a friction coefficient of UB. Now, they could be the same, but they don't have to. And we'll define the slope of our two blocks relative to the horizontal as theta. And so now A is the object that we want to lift. Object to be lifted, and B is the wedge. All right, very straightforward. Now, of course, you can imagine the shallower that this angle is, right? The smaller that theta is, the easier it's going to be to push the wedge underneath our block, but of course also the less distance that this block moves upward as we're pushing it, right? The steeper this angle is, the more this block is going to be lifted, but it also means that we'll have to use more force. And now we're going to go through and we're going to figure out exactly how much force we need. And to do that, of course, we'll do free body diagrams. We'll start with block A. All right, this is our block A. Right there. And what do we have? Well, we have that block will have a weight. Right? That's the whole idea. We're trying to lift this weight upward. So let's say WA. Now we have rollers left and right. Remember that whenever we take away a roller, we replace it by a normal force. Now if we're pushing the block to the left like we have right now, then we're going to push against these rollers and we're going to pull away from these rollers. So it means the rollers on the right will not have a force because, as you remember, the roller only takes up a force towards the surface, not away from it. So all that we have on normal forces up here is NA. We don't have friction in this direction, although this block is moving upward, right? So it's moving relative to this surface, but those rollers means there's no friction. Right? If there were friction, then if there weren't any rollers, if it was just against the wall, we'd have to add a friction force here. All right, so we have the normal force here. Now, if we're going to take away this block down there, we'll have to replace it by a normal force. Again, the normal force is acting perpendicular to the surface. We'll say this is NAB. And then we have a friction force in here. Now, we have to think about what direction that friction is pointed. And that, of course, depends on the direction of the movement, right? So the bottom block, block B, our wedge, is going to move to the left. That means that the friction force on this block on the top will point to the right, so to counteract it. If it acts to the right on the bottom, then it has to point towards the left on the top. So we'll have something that goes in this direction. This would be FAB. Maybe just to make this clear, let's do a little side sketch here. Right? So if I have my two blocks, if I take them apart, right, that's my top part, this is my bottom part. Right, this would be A, that's B. And so this block here is going to move relative to this surface, right? They're sliding past each other. This block is moving in this direction. That block is not moving left or right. It's only going up or down, right? So if this is moving in this direction relative to that surface, because that surface is stable, then I know that my friction force in here has to be pointing in that direction, right? Always opposite to where the movement is going to. If this one is pointing to the left, then of course to balance them out, if I stick them together, this one has to move the other direction. That's how we found that FAB was pointing in that direction. All right, now we have 1, 2, 3 unknowns. That is really one more unknown that we can deal with because we don't have any dimensions, right? So we can't do any moments. We can only do f of x, fx is equal to 0 and fy is equal to 0. So we have to add one more equation. And of course, that is that we know at impending motion in my surface between A and B, right? I know that FAB is equal to mu A times NAB. All right, so if I have that, I know I have 3 equations and 3 unknowns, so we can solve it. Turns out that we're not really interested in NA at all, so we're not even going to solve that. We're going to leave that out because it doesn't help us to determine what the force is that we'd have to apply to lift this block. But if we do sum of forces in the y direction, we'd be able to get started. So sum of forces in the y direction is equal to 0. What do we get? Well, we definitely get minus WA. That one's easy. And then we get both FAB and NAB have components. We'll do a little side sketch that we know where our angles are. This is my FAB, right? Then it's going to have a component here and a component there. And my angle would be in there. So if I'm looking for the vertical component, that would be that part right there. So that would be positive. So plus NAB, and now it is the adjacent one, so cosine theta. Maybe we'll put a NAB. And of course we can play the same game for FAB. Right, if this is FAB, there and there. Now the angle is theta is there, FAB. We're now interested in this component, it's going downwards, so we have to be negative, minus FAB, and it is the opposite. So sine theta. All right, we can see what we can do next. What else? Well, we can put in our law of frictions, right? So we can say that's equal to minus WA plus NAB times cosine theta minus FAB is mu A times NAB. Let's not forget sine theta. And then we can go ahead and solve this for NAB. Maybe we'll rewrite it to make it a little easier. WA plus NAB times, here it's just cosine theta, minus mu A times sine theta. That means we can solve for NAB by just dividing by that whole bracket. The WA is negative, so that's nice. It'll become a positive. WA divided by cosine theta minus mu A times sine theta. All right, so we have NAB, because again, WA is going to be given, the angle is going to be given. If we have NAB, of course, we have FAB, right? That was just mu S times NAB, which is then just what we have there. So we have mu S times WA divided by cosine theta minus mu A sine theta. All right, so we have both of those. That's all the information that we can get from the top block, from our weight, because again, we don't really care about NA. Right? We could do sum of forces in the x direction, and that would give us NA, but we don't really care for it. So next thing that we'll do is we'll do the free body diagram for our wedge. So let's see, our wedge would look like this. This is our wedge right here. Something like that. And what do we have? Well, let's do the easy one. We have P, of course, the force that's acting on it. We've taken away the surface at the bottom, so we have to have a normal force. Let's call it NB, and we'll have to have friction. Let's think about how this block is moving. This block is moving towards the left. So that means that the friction force is going to have to point towards the right to counteract it. So we'll have FB going to the right, and then we have to have the opposites of these. So obviously we have NAB pointing in that direction, and then FAB was going downward, so now it's going upward. Right, this is the same as what we did when we did frames, for instance. Right? FAB. And of course, we're at impending motion, so we can add our extra equation. Impending motion. So that would mean that FB is equal to mu B times NB, right? So this would basically, if we look at this wedge here, this would be one of those cases that we talked in the first section about how basically we have motion where all contact surfaces are at impending motion. All right, so what do we do then? Now we are trying to find what P is. If we look in the vertical and the horizontal direction, we have all kinds of everything. These two have components, but we already know those. We don't know FB, so we need to find NB first, so we'll have to do sum of forces in the y direction. So let's do sum of forces in the y direction is equal to 0. Is equal to what? Well, we don't have a WA in here. Maybe we'll just write this next to here. Usually neglect weight of wedge. And the reason is that's going to be very small compared to the block that we're trying to lift. All right, so we don't have a WB in this case. We will have an NB, so now we're going vertical, so that's going negative NAB. And it is going to be this leg right here, so NAB times, let's see, my angle would be up here, so times cosine. Then how about my FAB would kind of come here, so it'd be this part. So it'd be positive and sine. FAB times sine theta. And then what else? Oh, NB, of course. Going upwards. Keep on forgetting my coordinate systems. Let's add that one here too. Just so that the positive and negative directions actually mean something. All right, so with that, we can solve for NB because we know everything else. That means NB is equal to, that was negative, now it's positive, NAB times cosine theta minus FAB times sine theta. And then we already know what NAB is. That was up here. Stick it in there almost. So we'd have NAB. So that would then just be WA times cosine theta over cosine theta minus mu A sine theta. That was this block. And then minus F, so that's then mu S times sine theta times WA divided by cosine theta minus mu A sine theta. All right, and that looks like a nasty piece of business. Let's see though. We have a WA in both of those, so we can pull that out. WA times, the first one would be cosine theta. Also the bottoms are the same, so we can pull those together. So that's just cosine minus mu S times sine theta. Oh, that turns out to be quite easy. Cosine theta mu, why do we have an S in here? Getting myself moved around. These should not be S's. We started with an S here. This should be an A, of course, because it's up there. Let's see, where else do we have this? This should be an A, and that should be an A. There we go. A times sine theta. Of course, that's just 1. So that's WA. Which makes sense, right? I mean, the normal force here, if we don't allow this block to have any weight, should be just the amount of weight that's coming down. So that makes sense. That's good. Now, what else do we have? What else can we use? Well, now we have NB, so we can get FB. So I think what we'll do, we'll just do sum of forces in the x direction. Sum of forces in the x direction equals 0. What do we get there? Well, we get minus P. We get plus FB, which we know is just mu times NB. We'll get there next. So FB, so then we have NAB, that's going to go in the positive direction, and it's going to be the sine. So plus NAB times sine theta. So leaves me FAB. FAB is also going to be positive, and it's going to be the cosine. plus FAB times cosine theta. All right, so the only thing we really don't know is P, so we can solve for P and start plugging in all the other stuff. That means P is equal to FB. We said up here, somewhere, there, it's mu times NB. Mu B times NB. Then NAB, we have this long set right here, so that would be WA now times sine theta divided by cosine theta mu A sine theta. And then FAB is the same, just a mu A WA times, where do we have it, cosine theta. All of that divided by cosine theta minus mu A sine theta. All right, so let's see. That is a lot of sines and cosines. So NB we know is WA, so mu B times WA plus, we can pull the WA out of here, WA times sine theta plus mu A cosine theta divided by cosine theta minus mu A sine theta. Right, that's basically just pulling the W out, and then the two fractions we can just add together. So that means we can pull out a WA. So that would be the same as WA times mu B. And then that whole thing right there. Sine theta plus mu A cosine theta divided by cosine theta minus mu A sine theta. And that is the force that we'd have to apply to lift the block. If you go in and plug in numbers, you can say that see that this value is going to be less than 1. Right? So we have less force that we need to lift it than what we had initially in it. All right, so that was good. That was now what we would do if we wanted to lift this block up, right? If we're pushing towards the right element. Now what happens if we're pulling to the left instead? Well, we're pushing to the right, now let's pull to the left. Well, what changes? Well, the big changes that we'll see, well, first of all, of course, our NA will be acting on the other side, right? Because now this block is moving in that direction, so it's pushing against this wall instead of that wall. And of course, the movement directions are going to be flipped around, so all of my FAs are going to change directions. Right, so let's do what changes if force P is acting to the right instead. Well, again, we would have to change our free body diagrams. We'll do them smaller here. Not going to go through all the steps again, because that's a lot of sines and cosines to play with. Right, so now we said we're now pushing towards the right hand wall, so we'll have our NA is going to be acting in this direction, NA. Our WA, of course, still pointing downwards. WA, we don't have a force there because it's pulling away. Then we'll have our NAB, that's not changing. NAB, and we said that our friction force is going the other direction, right? Because now all the movements are going in the opposite direction. So that'd be here. And then if I look at my wedge, draw that next door. Oops. Like that. Then I have my NAB. NAB, I have the friction force going downward, FAB. I will have my normal force down here, which is NB. And then this block is now moving towards the right, so my friction is going to act towards the left. FB. And then, of course, my force. P. And now we can go through all this and go back and do the same analysis. Basically, all we have to do is flip some signs around. When we do that, we find that P is equal to WA times mu B plus mu A times cosine theta minus sine theta divided by mu A times sine theta plus cosine theta. That is now our force that we have to do. We have to pull on it, right? So it's not a huge amount of change. Basically, all we do is we flip the sign of the sine, right? The sine theta here is positive, here it's negative, and we change some other signs down there as well, right? The cosine here was positive, the sine here was negative, and it's now positive. But otherwise, the system is the same. Now, one more thing before we finish, and that's the concept of what's called, let's put the word down here, self-locking. What does that mean? That means that I would not have to hold the block in place. Let's go back to our main picture here. That's the idea of a self-locking wedge, is that if I take this force away, the wedge is not going to be pushed out. Right? So that's, of course, if I'm actually trying to lift this is very convenient to do, because I can push this block in a little bit, reset everything, push the block a little bit more, push a little more without having to worry that the block is going to come back out. Right? So that's the idea of self-locking thing. Now, if I want to find out if it's self-locking or not, I can go through all this exercise, and if for this scenario here where I'm pushing against the block, if the value comes out to be negative, then I know that to actually get impending motion, I would have to move in the other direction. So that would give us that will allow us to check if it's self-locking or not. And we're going to talk in more detail about self-locking once we get to the next section, which is going to be screws. But just to summarize here, where we talked about wedges, where the idea is that we can use a much smaller wedge to lift a heavy object upward. We can use it to split wood and all that kind of stuff. And to figure out how we do it, we basically take the two blocks and we do free body diagrams of them, and then just go through and figure out what the force P would have to be to lift up this block.